Hello, everyone. Welcome to the Temporal Graph Reading Group today. We are very glad to host Louis from Renmin University of China, who will be presenting their recent work, TGB SEC or TGB Sequential.
Stick
Um,
is okay.
yeah,
Yeah.
and challenging temporal GNNs with complex sequential dynamics. And in terms of our speaker today, um, so Louis is a PhD candidate at the Algo Lab at Renmin University of China, supervised by Prof. Zhe Wei, and she received her bachelor degree in computer science and technology at Beijing University of Post and Telecommunications in 2022. Her research interests include dynamic graph learning, graph unlearning, and efficient graph algorithms. So I will hand the mic to you.
Yeah. Thank Andy. Thank for the kind introduction. Hello, everyone. Welcome to my talk today. Thanks for your coming. My name is Lu Yi. I'm currently a PhD candidate at Renmin University of China. Today, I'll be presenting our work, TGB-Seq benchmark challenging temporal GNNs with complex sequential dynamics. This paper has been accepted at ICLR 2025, and I'm currently in Singapore to attend the conference. So if you're also at ICLR, I'm very happy to arrange a time and we can meet at the conference. Yeah, let me start the work. To be short, our work proposed a challenging benchmark for future link prediction with a focus on complex sequential dynamics. Let me change the pointer. Here is an outline of what we'll cover for today. First, the background on temporal graphs and temporal GNNs, and then the limitations of existing methods and datasets, and our proposed TGB-Seq benchmark, and finally, the benchmarking result on TGB-Seq benchmark. Now let's start with some background information. First, the temporal graphs. In temporal graphs or dynamic graphs, both edges and nodes evolve over time. For example, in social networks, new users join in the network and new connections between the users form. And in recommendation networks, users purchase and review products over time. Temporal graphs better capture the evolution of graphs as they evolve in the dynamic system in real world. Compared to static graphs do not account for the temporal evolution of graph over time. Temporal graphs are generally categorized into two types, the discrete time and the continuous time temporal graphs. A discrete time temporal graph is a stream of snapshots, G1, G2 to GT, and each snapshot may introduce many new nodes and new edges. And a continuous time temporal graph is a stream of edges, each associated with a exact time step, capturing the continuous evolution of the graph over time. Temporal GNNs could serve many tasks, but in this work, we focus on the future link prediction. The goal of future link prediction is to predict whether a link between two nodes will form in the future. Specifically, given a graph G, a source node S, and a source node D, and time step T, and all the edges before time T, the model is asked to predict the likelihood of the edge SD appearing at time T. This is a very critical task in many real-world applications like recommendation. In the recommender system, the platforms will suggest products for users according to their previous interactions. For example, click a product or add to preference, add to car purchases, and so on. Future link prediction is often framed as a ranking problem that the model is asked to rank the positive destination node D higher than other K negative destination nodes that we sampled for the model. Now let's move on how temporal GNNs work. Most existing methods include two core modules, the memory module and the aggregation module. The memory module aims at updating the node memory according to its previous memory and the interaction history. And the aggregation module is responsible for aggregating historical neighbors and generate the node embedding. Some models further introduce a high-order correlation module. This module will consider the relation between the neighborhoods of the source node and the destination node. For example, the TGN will use a GRU to update the memory and use attention to aggregate the historical information. On the other hand, EdgeBank, the heuristic method, simply memorizes all historical neighbors for nodes. And Digiformer, one of the state-of-the-art methods, use attention to aggregate historical neighbors, and it further introduce a high-order module by calculating node neighbors frequency. Now let's move on to motivation. Our work is driven by two key observations. First, we evaluate existing temporal GNNs on these four widely used datasets: Wikipedia, Reddit, SocialEvo, and Run. And we evaluate these methods on these datasets by predicting seen edges and unseen edges. The bar here, without shading, represents the MRR scores of these methods predicting seen edges. And the bar without shading here represent the MRR scores of predicting unseen edges. We observe a huge performance gap between predicting seen edges and unseen edges. And our second key observation, we evaluate temporal GNNs on two recommendation datasets, Google Local and MovieLens. As recommendation is a typical downstream application of temporal GNN, right? So these models are expected to perform well on these two datasets too. However, we find that comparing to SGN-HN, a sequential recommendation method, temporal GNNs far significantly behind SGN-HN. Here for the SGN-HN, and these are the temporal GNNs performance. And comparing to their performance on Wikipedia and Reddit, two widely used existing datasets, their performance on Google Local and MovieLens exhibit a huge performance degradation. So, why do these models fail on recommendation dataset, and why does this performance gap occur?
Uh,
We
just a quick question. What
yeah,
is the
yeah.
SGNN model?
Yeah, it is a sequential recommendation method. We select it just because we find that it can perform well on Wikipedia, Reddit, and Google Local and MovieLens, both, all of them. And other recommendation methods can perform well on these two the recommendation datasets too. And SGN-HN is a random choice.
Okay, okay. And the Digiformer doesn't really exist for ML 20 million because it didn't scale, right?
Yeah, it out of memory.
Okay, yeah, makes sense. Please continue. Thanks.
Yeah, thank you for your question. And if you have any question, can just stop me like this. Yeah.
Okay, thank you.
So we dive into the existing data sets and want to examine why this performance gap occur. We find that existing data sets contain excessive repeated historical edges. For example, the Wikipedia dataset, they follow such a repeated pattern as depicted in this figure. A node will keep interacting with the same node again and again and again. So this allowed the temporal GNNs to take shortcuts. They just memorize the historical edges and can perform well on these datasets. For example, the Edge Bank. They perform well on many datasets, but they only memorize the historical neighbors of these nodes. And Digiformer, it calculates the frequency of interaction between node pairs. For example, U1 here interact with A 3 times, but U1 has never interacted with item D. So Digiformer can predict that U1 is more likely to interact with A instead of D. This shortcut contributes a lot to the performance of Digiformer, and this explains why this performance gap occur. The repeated edges dominates these datasets and leads to the overfitting to these repeated edges and underfitting to these unseen edges. Right, let me move on. To further investigate the shortcomings of temporal GNNs, we built a toy example consisting of users and items. And in this toy example, the first user in group U, U0, first interact with I0 at time 0, and then I1 at time 1, I2 at time 2, I3 at time 3, and time 4 at time I4 at time 4. And the first user in group B interact with I5, I6, I7, I8, and I9 from T0 to T4. Note that the interaction times for V0 are the same as for U0, both from T0 to T4, T0 to T4. And the other users in group U and group B follow such a pattern to interact with items. At subsequent time, like T5 to T9 and so on. And so in this toy example, users in group U will interact with items from I0 to I4, and users in group B will interact with items from item 5 to I9. And for each user in group U, there will be a user in group B that interact with items at the same time steps as that of the users in group U, but they interact with different items. So the test sample is given where a query user interacts with I0, I1, I2, and I3. Then we ask the model to predict that whether the query node will interact with I4 or I9 at time t, based on these previous interactions. So here's the results of existing methods on this toy example. And almost all the methods here achieve only 50% of the average precision. That is, all the methods fail to rank rank I4 higher than I9. So all these methods cannot capture such simple sequential dynamics. That is, a user who interact with I0 to I3 will interact with I4, and users interact with I5 to I8 will interact with I9. They cannot capture such simple dynamics.
Just a quick question, if you don't
Oh,
mind.
yeah,
Uh,
yeah,
so yeah, so definitely very interesting. But so for the I1, so I0 to I4, is there a
yeah.
specific feature that tells you that they are, ordered in this sense, or how does the
Yeah,
model know that like I4 is I4, for example?
Yeah, that's a very good question. They have no distinguishable features. Also, the edge feature is blank.
I see.
So
Yeah.
yeah, we cannot just like many methods, the model design they do not know which one is I0, which one is I5, except for their distinguishable feature. But this distinguishable feature are often blank in many data sets.
Okay, so the only information they have is they know that this U1
Yeah.
has interacted with like the I0 to I4. So okay, I see.
Yeah, the only information is the interaction history. They know that some user there is an ID in the interaction database, the data set we got, but the model cannot distinguish these nodes if they don't have distinguishable feature.
Yeah.
They only can they can only distinguish these nodes by their interaction history.
Hmm.
Yeah.
Yeah,
Mm.
that makes sense. Yeah, thank you.
Yeah. Thanks. Let's move on. So, why did these models fail on this toy example? As explained, um, just we just explained this, but we can elaborate on it more. So, as mentioned earlier, the memory module and the aggregation, the models often include the memory module and aggregation module or both. The memory module will take the no memory, no feature, and the last interaction history as input, right? And the last interaction information include the node memory of the destination node and maybe their feature and the edge feature and the time interval between the current prediction time and the interaction time. So since, as we mentioned, there are no distinguishable features of nodes and edge. So, and the timestamp of the users in group U and group B, they interact at the same timestamps. So the memory module will generate the same memory for I4 and I9. The aggregation module generates the embedding for nodes, and it takes the no feature and its no feature, no memory, and its K-hop neighbors information as input. The K-hop information include the feature feature of the destination nodes and edge feature and time intervals as well. K here is typically set 1, that is, we often consider one hop neighbor in, in most models. And however, as we mentioned earlier, they interact the one hop neighbor of I4 and I9, that is the users in group U and the users in group V. They always interact at the same timestamps and they lack distinguishable features. So the embedding of I4 and I9 is the same too. So let's come to the high order correlation module. Intuitively, the high order correlation module can enhance the performance of temporal GNNs, right? Because I4 and I3 or other neighbors of the query node, they have co-neighbors because there are many users in group U. They interact with these items and item 4 together previously. However, I9 and these items, they do not have any co-neighbors. Since here and here, they are totally different communities and they don't have any interactions. However, in this case, we find that even include high order correlation module, it does not help very much. For example, we enlarge the length of the temporal random walk of call, and the average precision slightly improved from 50% to 52.8%. There is it does not help, and why was that? We think it might be due to that the high order correlation module introduced too much noise, and the module cannot leverage effectively the information we mentioned here. That is, I4 and these items have co-neighbors, but I9 and these items do not. They cannot leverage effectively. So all the modules here cannot distinguish I4 and I9. They fail to capture the sequential dynamics in the TOEIC example here. However, this such sequential dynamics is not unique in this TOEIC example. Actually, this kind of sequential dynamics are everywhere in many applications. For example, in a movie watching network, someone interested in Harry Potter, she may first watch the first installment, the Sorcerer's Stone, and then the second installment, the Chambers of Secrets, and then the third one, right? And in a social network, someone interested in the progress of large language model, he or she follow OpenAI, Anthropic, and he or she will follow Mentor. And in an e-commerce network, someone who has purchased a mobile phone, a phone shell is likely to buy a screen protector next. So understanding complex sequential dynamics is the key to this future prediction task. However, existing datasets have a high repeat ratio. There are too many repeated edges in the dataset. That is, their sequential dynamics are overly simplistic. And existing methods have already achieved great performance on this dataset. We need more challenging datasets to push the development of temporal graph learning. So we propose TGB-Seq, a new challenging benchmark. All the datasets here have a low repeat ratio, as shown here, and they are curated from diverse domains, representing typical real-world application of future link prediction. And they all follow a power law degree distribution, as shown in these figures. And they range in size from medium to large. These properties make them more realistic and challenging. Now let's move on to the benchmarking results on TGB-Seq. Here's the result for bipartite datasets. SG and HN again, the sequential recommendation method, as mentioned earlier, it outperforms all temporal GNNs on these bipartite graphs. And the memory-based module, Judy and TGN, outperform other temporal GNNs in contrast with their performance on Wikipedia and Reddit. And Digiformer and Call outperform other temporal GNNs on Wiki and and Wikipedia and Reddit, but failed to perform effectively on TGB-Seq bipartite datasets. And on non-bipartite datasets, SGN-HN does not apply, and the performance of the temporal GNNs varies across these datasets. Almost all the methods rank in the top 3 on at least one dataset, but no one dominates across all datasets. So these results highlight the need for more capable temporal GNNs that can handle diverse and complex sequential dynamics. Let's move on to training efficiency. We test existing temporal GNNs on 3 datasets, small size, medium size to large size. The most efficient methods are GOD, direct, graph mixer, and then TCL and TGN. And TJT, digiformer, and CON, their aggregation module includes some complex design, so they are not efficient enough. And digiformer and CON even cannot finish a training epoch in 24 hours. So we denote OOT here.
Um, I
Yeah,
think for these models, the TGAT, it's because the temporal neighbor sampling is very expensive. I
yeah,
think it
yeah.
samples like, because it doesn't have a memory module, so it requires you to sample constantly to get past neighborhood. And digiformer, it's because the common neighbor, so the higher order stuff you were talking about, but it's just
Yeah.
computing some edge specific feature. And same with CAWN, it's also computing these features. So it's
Yes, yes.
the additional computation they are doing that's making them very slow. Um,
Yeah, yeah. They include some complex design and needs very much computational cost.
yeah,
Yeah.
yeah, thanks.
Thanks for that. So to conclude, our work is motivated by the limitation of existing dataset and yeah, we are motivated by the limitation of existing datasets. Existing dataset contain excessive repetition of edges, and existing methods fail to capture complex sequential dynamics. So we propose TGB-Seq datasets. They exhibit complex sequential dynamics and minimal repeated edges, and they are curated from diverse domains from real-world tasks. And the benchmarking results underscore that the need for more capable methods are needed in our field. Here is our website for TGB-Seq, and as you can see, you can find the leaderboards and documentation on this website. We have established leaderboards for each dataset according to the benchmarking results, and we also build a pip package. You can simply install it and start to use these datasets in a few lines of codes. This get started page shows the simple usage, and we welcome anyone to submit your results on this leaderboards, and you can find the submit link on the website. Fine, let me move on. So that's all for today, and thank you for all your attention. So now I'd be happy to take any questions. Let me think the
Yeah,
chat.
yeah, thank you for the great presentation. So if you have any questions, feel free to type in the chat or just like unmute yourself. And yeah, and thanks for the great presentation. So I think it was very clear. I think the sequential dynamics part is very interesting and it's kind of a new direction that the existing models don't really work on. Um, yeah, so
Thank
I
you.
think
Thank you.
it's quite interesting. Yeah, unfortunately, I cannot go to iClear for this time.
Oh, sorry for that.
But yeah, so
Mm.
yeah, so we also have the KDD like workshop. So if you have something, submit there, so we can also meet there. But
Oh, wow. Okay. I'll see. I'm not sure I have enough work to submit.
well, technically
Mm.
it's non-archive, so you can also submit something in progress or some of
Oh, yeah.
existing work. It's non-archive, so it doesn't really count as a publication. So um, yeah. Um,
Okay. Thanks
but
for the opportunities.
yeah.
Yeah.
Um,
Mm.
yeah, so I do have more questions, but is there any
Oh, yeah.
questions from the audience? Um,
Yeah, I have a question, and I think that was kind
Oh,
of along the lines of what Andy asked before. So, if you can go back to the example where you have the two communities that interact with the different groups.
yeah. Here.
Yes, exactly. The slide. So, I was kind of thinking about, okay, you said something that they have distinguishable features, or that maybe the nodes have IDs as a feature, or could you explain a bit again why it is and kind of what?
Yeah. 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 Um, Let me dive into this part. For example, the memory module will take the memory of the node feature. The node feature, as we explained, they are all zeros. And the edge feature here are all zeros too, since these nodes and edges lacks the distinguishable features. They don't have that. So this part and this part are all zeros. And the memory module can only find out the difference between I4 and I9 by the time step. However, these two communities always interact at the same time. Just like this, U1 here interact with I0 to I4 from T5 to T9. And there is always a user in group V. It will interact with items from I5 to I9 at the same times as that of U1. So I4 and I9 in the memory module, they cannot generate distinguishable memory for I4 and I9 since the time steps for I4 and I9 is always the same. Yeah. Um, do I explain correctly?
Yes, so I think I understood, how some of
Mm.
the modules fail to, but how does your method kind of differ from that? How does it account for that when there's kind of no real features to use?
Yeah, so if you want to distinguish I4 and I9, so there must be something different for I4 and I9, right? Um, we know that his interaction history is not the same as they are two totally different communities. So in the module, there must be some part. Um, uh, it may be learnable or it may be just like the high order correlation module. It can find out that I4 and these items have co-neighbors and I9, and they do not. So in the SGN-HN we use here just as a random choice sample. So SGN-HN will use learnable embeddings for each items and users. Um, it is something like in the literature of graph embedding. I'm not sure it is familiar for you. So there are learnable embedding for each item and user here. So when the model learning the interaction for items in user, the embedding for them is learnable and it changed by backpropagation. So in this progress, they will aware that these embeddings for this group, they may be similar, and this embeddings for this group may be similar, but this two group is totally different in terms of their embeddings. So they can find out that I4 is and I9 are totally different.
Does that including these, I'm not sure if it's shallow embeddings or what type of embeddings you're using here, but does that do anything in terms of inductive versus transductive learning? Like, will
Yeah.
this also be able to account for new nodes and so?
Yeah, that's a good question. So in all this data set in TGB-Seq, we only consider the transductive task. So we remove all new nodes in the test stage. In the test stage, all edges we are seen during training. So, in our opinion, transductive tasks and inductive tasks are totally different, and they should be studied in totally different way. Because, for example, in recommendation systems, a new user join in the e-commerce platform, so we do not have any interaction history of she or him. So we cannot we cannot recommend products according to its preference. We only can recommend she, her, or him some items that are popular for most people. So we think inductive and transductive are totally different tasks, and they should be handled with totally different methods. So in this work, we only focus on the transductive. Yeah.
Okay, cool.
Yeah.
Yeah. Thanks.
Yeah. So
Thanks
that's
for
a
the question.
Of course.
Yeah. So I think it should be a good future direction for the inductive and transductive both, and we only focus transductive here.
Yeah, that makes sense. So, so actually on that topic, there's a previous work. I think it's called Pop Track. I think it
Pop.
was at Europe's 2022 TGR workshop or 2023. I forgot which one. But it's basically a heuristic like EdgeBank, but it's
Yeah.
working for inductive learning where it basically just recommends recent global
Yeah.
popular item. So
Yeah.
so I don't know if you have it on the leaderboard. I think it could be an interesting baseline just to see because it should definitely perform better than EdgeBank because EdgeBank is not designed for this
Yeah.
inductive task, like the
Yes, I think it may be a good baseline. If but I'm not very sure that since these data sets are much large and it may be a little difficult for a simple popular baseline, but it is a good question, and it may be a good try. Yeah.
sounds good.
Yeah. Um, I think it may be a very good start point for inductive tasks.
Yeah, because
And
it's basically the cold start problem, right? What you describe is the cold start problem where you don't know
yeah,
anything about
yes,
the user, right?
yes,
Um,
yes, yes,
But then the
yeah,
model, like as soon as you observe a few edges from the model, like you have a few interaction from the user, in the ideal case, your model should be able to then start to infer. Basically, your prior on the user becomes more and more biased
yes,
towards the user's personality. So then you can make better and better predictions. So, um,
yes,
so I think yeah. So the inductive node side would be interesting as well here. Um, and yeah, so I have one more question, but is there any other question from the audience? Uh, okay. So then I will go ahead. So I think the example that you showed is quite interesting. Um, so have you thought about doing maybe like a theoretical extension of the work, like focusing on trying to understand the expressiveness of the sequential dynamics, like how expressive are the different category of current models in terms of how they learn these sequential dynamics, right? So I think empirically you show that they all don't work very well, but
Yeah.
in a theoretical sense, yeah, so should they be able to learn it, or it's just that by design they cannot learn it? Like, so for example, for CWN, I think theoretically it should be able to know this, but in terms of learnability, it's a different thing. So
Yes. Sorry, I want to make sure, are you asking that why CWN cannot deal with this two example, but it is expected to
yeah,
be able.
so theoretically
Um,
it should be able to, yeah.
yeah, that's a very good question. There is another work called, let me think, maybe there's is a work published in LG, Learning on Graphs, and it takes it enlarge the it takes K-hop neighbors into its consideration. It um it's based on digiformer, but digiformer considers only one of the first hop neighbors, right? But that work consider K-hop neighbors in their model design. So in this case, um, that method is expected to able to handle this toy example,
Mm,
but I don't try it, and I'm not very sure the actual performance of it. And Kao here we enlarge the lens, but it does not help much. I think I think, but I'm not very sure why, the exact reason. But I examined their random walk embedding encoding, and I find there is too much zeros in their embeddings of the temporal random walk. It may be due to most information of the high order module of CAWN. It makes nonsense, and they are noise. They are totally in the noise. So
I
it's
see.
hard for CAWN to leverage such a simple information that these co-neighbors. It's hard for it to leverage such information uh, by removing such noise, right? So it just simply improve a little.
Yeah, so maybe a good direction is to actually maybe modify it or design better models that to can get rid of the noise, basically just keep the meaningful information. And also there's
Yeah,
the NAT paper. I don't know if you know the NAT paper.
NAP.
So so the NAT, NAT, I think it was tested on TGB as well. So that one also look at joint neighborhood features. So kind of
Yeah,
similar to CAWN. I don't know if that one works or not, but yeah, so I think it's a like interesting question. But here you can see that when you increase the length, the performance does improve. So 50% is completely random, right? So
yes,
52% means it start to learn something. So expressiveness wise, it is doing something, but it's just that it's not easy for the model to learn, as you mentioned. So I think it's a quite interesting observation. So
yeah. Yeah, thanks. There is another difficulty for your mentioned that direction. When we enlarge the length of the temporal random walk to 3, CWN occurs out of the memory. We use
right.
80 GB GPU, but it is out of memory. So I think it will be difficult, but promising to try in this direction. Yeah.
Right. Yeah. Yeah, thanks for sharing that insight. Yeah, so I know that it's more a problem with the model's code efficiency and implementation. Not necessarily mean that you cannot run it, it's just that the code was not written in the most scalable way. Similar with digiformer and stuff. So they are, yeah. So that's would be, yeah.
Which one?
So like, for example, TGAT and digiformer and CWN. So you run these,
All
yeah.
of them is out of time.
Yeah, so it just takes
And
too long, right? It's not optimized for scalability.
yeah,
Yeah.
yes, it's very, very long that they cannot finish one training epoch in 24 hours. So we have to
Yeah.
stop it.
Yeah, that makes sense.
Yeah, none of them is out of memory since they often consider one-hop neighbors only. Yeah,
Yeah. Thanks.
thanks.
Yeah,
Yes.
and thanks for the discussion. If there's no more questions, we can wrap up the talk here. And thank you for joining, everyone. And thanks for the great presentation from our presenter today. So yeah, enjoy iClear and yeah, have a nice
Yeah.
conference. Yeah.
Yeah, let me turn to the last page. Yeah, our poster will be presented at 3 p.m. to 5:30 in April the 26th and at 184 in Hall 3 and Hall 2B. So if you are available at the time, please feel free to reach out and we can also arrange another time if you are unavailable at that time. And happy to set up another time to meet in person with you as well. And thank you, Andy, for organizing this section, and thank you all for coming to my talk today.
Yeah. Thank you. Thanks.
Thank you very much.
See you, everyone.
Thank you.
Thank you.
Bye.
Bye.